Hi guys, Buildzoid here, and so today I'll just be sharing my thoughts on safe voltages for static Ryzen 3rd Gen overclocks. And this is just going to be a really long video because this is just a really complicated topic. So let's start with a bit of a history lesson, I guess. So with Ryzen first gen, AMD straight up came out and said, stay below 1.42 volts and you'll be fine. And so that's what everybody in the overclock, like the majority of people in the overclocking community just kind of followed that advice and stayed below 1.42 volts for their static overclocks. Then for Ryzen 2nd gen, AMD didn't say anything, and unfortunately the recommendation for 1st gen doesn't work anymore because 2nd gen is on 12 nanometer, which is not the same as 14 nanometer. 12 nanometer clocks higher, but it also pulls significantly more current at the same voltages, and so, it's like, yeah, you can't really run it at the same settings anymore. So the workaround for the fact that AMD didn't tell us what kind of voltages are safe was, let's just see what the CPU's own power and lifespan management system decides to run under worst case scenario. And for 2nd gen CPUs, that'll generally be around 1.375 volts. If your cooling system is bad enough, the CPU will actually sort of throttle itself down to even lower voltages to make sure that its lifespan doesn't get degraded. Lovely how your CPU has a built-in voltage recommendation tool, isn't it? And then for 3rd gen, I think this methodology still holds true, but with 3rd gen, it gets a bit more complicated because while 7 nanometer is much more thermally dense than the previous two manufacturing processes, so the CPUs are harder to cool. The CPUs also now have full-speed AVX256 support, which basically means they are capable of crunching far more numbers at the same time than ever before. And well, if you're doing more work, you're going to be making more heat. So the chips now, like basically 7 nanometer is already kind of a cooling problem from just it being 7 nanometer, and then you add AVX256 to that, and it's just like, oh yeah, this runs really freaking hot. And also the process variants might be kind of all over the place. So I ran a bunch of tests with my 3950X and my 3700X, and the 3950X is faking being a 3900X and also faking a 3800X by disabling cores and CCDs, so that I could get some basically voltage data that is just reliant on the lifespan and power management system from that's built into the CPU from AMD. So we're just using the fit limits essentially. Like that's what the fit feature of the CPU that you hear referred to. You can basically think of that as the CPU's own lifespan management system. And this is designed to make sure that your your CPU, at the very least, outlasts your warranty. More realistically, I'd expect it to be designed to keep the CPU at, in a functional condition for like 10 years, because that's generally what you would target with your. I think that's just a general guideline in the semiconductor industry that I might have, stumbled across while doing some reading somewhere. Because you also have to consider, like, if some manufacturer of like a system integrator wants to build a Ryzen system and offer a 3 or 4 year or an extended warranty on it, they're going to be really upset if AMD sells them a CPU that dies in like 2. Right? So, from a business perspective, you're not going to make a CPU that literally dies an hour after the warranty is over. That's a terrible idea, even though theoretically you could probably tune the CPU's built-in lifespan management system to do just that. AMD, like Ryzen's, have a ridiculous amount of temperature sensors, current sensors, voltage well, okay, not actually that many voltage sensors. The SVI2TFN reading is literally just asking the voltage controller what voltage it's supposed to be at. But there is a lot of power management and monitoring systems built into these CPUs. So, if you misused all of that functionality, you could theoretically build a CPU that up and dies in 2 years, in a very controlled manner. I guess it could also just go like, oh, I'm 2 years old and blow itself up, like potentially that too. But you wouldn't do that. So, as with 2nd gen, we're just using the voltage behavior of the CPU within the realms of the boost system to judge safe voltages for static overclocks. And what I find the most interesting, and so all of this data here is gathered using an oscilloscope hooked up to the DyeSense of a Gigabyte X570 Aorus Extreme. I was using the Aorus Extreme because it has the most vanilla implementation of AMD's boost system. Like ASRock, I have like the PBO on the Tai Chi has some very strange behavior. Um, to the extent that there's as far like you shouldn't try messing with it. Like I don't know what it is really weird. So yeah, the X570 Taichi just has some strange PBO behavior in general. The MSI motherboards, for whatever reason, can't run my 3700X in Prime 95, either because MSI is violating some AMD specification or because that CPU is actually degraded. I have no idea if it's actually degraded because I don't actually have data proving that that CPU ever functioned, like ran Prime 95 when I first got it. I think it probably did. I find it kind of hard to believe that I never ran Prime 95 on that CPU until like a couple months ago, but I don't have proof of that statement, so I can't say for sure that I haven't degraded it or that the motherboards aren't just doing something very strange with it. But either way, the 3700X does work on the Gigabyte and the ASRock boards and the Asus boards. It's just the MSI ones that can't run it, so the MSI boards were not an option for this testing. Not that I've noticed anything particularly strange in terms of their like voltage behavior. That seems to be exactly the same as all the other boards. It's just that like the thing that I think is like the strange behaviors with some of the boards is, well, the Taichi seems to just straight up violate AMD's power specifications right out of the gate. So that right there is just like, well, it's ASRock, you know. It's not as bad as some of the other things I've seen in the past, but it's annoying. But then with like, but basically I've not seen any like boards significantly violate like the voltage specs. It's mostly seems like the MSI boards are doing something to the frequency to run Everslow slightly faster. And that's what's causing that 3700X to crash on them because that chip sucks. Which might be because it's degraded, or it might have sucked the entire time, and I really have never checked Prime 95 on an MSI board with it, but I have no proof of that. Anyway, so I did all of this testing on the Gigabyte board because that one just, well, one, it was also set up for the testing, but also Gigabyte's implementation of PBO is just the least weird, like, it does the least strange stuff. It's been kind of the most consistent, even as strange as PBO is in and of itself, because it's AMD software. Like, you expect it to not change behavior with updates? Like, are you new to this? Does nobody remember first gen Ryzen where every BIOS update would like drastically change memory overclocking capabilities? So, yeah, like that's, I'm not thrilled with having to rely on such unreliable software, but at least on the Gigabyte motherboard, it doesn't see like the Gigabyte at least doesn't, add any of their own sort of flavor to it, which just throws it off more, in my opinion, which is a real concern with some of the other board vendors. So now I use the oscilloscope for gathering all of these voltages, though the voltage data that this voltage data is basically in line with, and I say basically because if you use the SVI2 TFN sensor in hardware info, it's going to have a resolution of 6 millivolts, whereas this has a resolution of 10 millivolts. So obviously, if you use hardware info, there'd be a little bit more detail, but the actual voltage measurements are the same, and the oscilloscope is just far more convenient for gathering data than hardware info is. So I used the oscilloscope because I already had that set up. I did still use hardware info for getting some like temperature checks and that kind of thing done. So that's the test methodology explained, I think, right? And then I just ran Cinebench, and this is how many threads I ran, and these are the PBO settings, so 333 watts, 230 amps, 230 amps for the EDC and TDC, because if you set anything else for the EDC and TDC, Prime 95 is not going to run correctly. Or more like, if you set anything lower, Prime 95 is going to run slower and at lower voltages, which means you're not hitting the fit limit anymore. It's also worth noting that if you're running Prime 95 and your voltage starts coming down over time, it's because your cooling system is not good enough. So the CPU literally has a built-in upgrade your CPU cooling system function, which is like, I appreciate that. So yeah, like this voltage initially started out at like 1.22 volts. But over the span of a couple minutes, it crawled down to 1.19 volts because the CPU was approaching 90 degrees. So actually, I think it eventually even hit, like, was occasionally, like, straight up hitting 90. Um, so, yeah, if you're running Prime 95 and you're getting a really low voltage reading, it means your cooling system sucks and you should get a better cooling system. That's what the CPU is telling you. It's also why you probably shouldn't be doing a static overclock, because obviously high operating temperatures lead to more high operating temperatures lead to more leakage current. They also make the CPU more susceptible to electromigration in general. Basically, high temperatures are bad for your CPU. Okay, so like that's why the voltage comes down as the temperature goes up. Right, that's why the lifespan management system even has that behavior built in. Because if CPUs didn't degrade with temperature, there's nothing stopping the CPU at running like 1.4. Like theoretically, the CPU could just run whatever voltage up to whatever infinite temperature, right? Which yeah, that like the voltage comes down because the temperature is too high. Anyway, so what I find most interesting with this data is the difference between the fake 3800X and my very real 3700X. Because the fake 3800X refuses to go above 1.25 volts, no matter what. Like, it just doesn't go above 1.25 volts. Oh, and also, I forgot to mention, the reason why there's no 10x scalar data in these charts is not because I didn't take it. I did take it, but it's because the 10x scalar does some very strange things. Like, light load, it doesn't do anything, right? Like, if you're running one thread of Prime 95, it doesn't do anything. If you're running 32 threads of Prime 95, it doesn't do anything. But for some reason, if you run 32 threads of Cinebench, it makes a very small voltage increase. But if you run 16 threads of Cinebench, that's a pretty major voltage jump. If you run 12 threads of Cinebench, it's an even bigger voltage jump. And we see similar strange behavior with like the 3700X down here, where it's like 1.41 on 1X and then 1.42 on 10X, or 1.36 versus 1.4 on 10X. And it's just like, so first of all, we don't actually even need to go all the way up to 1.4 volts, in my opinion, because we still need to droop down to this voltage somehow. Right, so it's just like, okay, there's no point having the option to take the idle voltage that high up, so we don't need that. And the other thing is like, this is just very strange that it is boosting like low thread count, like low load workloads with voltage that much. It's just like, it doesn't make sense to me. I wouldn't consider it safe data. So if anything, maybe going with the 1x scalar for all of this voltage comparison data is maybe overly safe, but I'd say most people don't want to have their CPU blue screen randomly after a year of runtime. So because that's the thing, is like, if your chip degrades, you're not going to notice it until it's in such bad condition that it starts crashing in your day-to-day usage. And that's obviously not something you want to be dealing with, you know. And I speak from experience, because I had a 3960X that I ran at pretty high voltages for about a year. And well, initially I had a really nice stable 5 gigahertz overclock. I could run IBT, I could run Prime 95, I could run Intel's Intel's XTU stress test. You know, I could run all of the things. And then after about a year, I was really annoyed that it's like, why can I no longer pass any of these stress tests at the exact same settings? And it's like, well, it's probably because you were running 1.53 volts into the chip for about a year. Also, that chip was water cooled and never went above like 75 degrees. So it wasn't like I was running it cold, but I was just giving it way too much voltage. And it took about a year before I really noticed that, hey, yeah, this chip just doesn't do 5 gigahertz anymore. And it also, like, the thing is, it destabilized all of the previously lower frequency overclocks as well. Like, 4.5 gigahertz initially worked at 1.35 volts, and after that year, it didn't work at 1.35 volts anymore, so that needed more voltage. So just, it takes degradation, depending on how much you're going over the recommended voltage. It can take a couple, and also it depends on what kind of workloads you run as well, right? If you do very heavy, high current, high heat output workloads, you're going to notice the degradation very, very quickly, assuming that you're, you know, well outside the the safe voltage range. Whereas if you're running, Whereas if you're running very light workloads and you're outside of the safe voltage range, even for the lighter workloads, because the thing is, degradation is a function of like temperature, current, and the voltage itself. And I have a video talking about all of the various factors that go into degradation. So I'll link that in the description. But anyway, because of that, you can like how quickly you can degrade a CPU can go from basically a matter of hours to several years, depending on a variety of variables, right? And so it's really hard to go like, oh no, my 2 months, my overclock is stable. Though it is more noticeable, like degradation will be more noticeable if your overclock is really on edge to start with, right? So if you start with an overclock that's like super micro optimized, where there's only like 5 millivolts, like you can't even lower the voltage another 5 millivolts before it stops passing stress tests, then obviously you're going to notice the degradation. That'll also help you notice the degradation sooner because, well, if the chip degrades by 5 millivolts for your given frequency, that's how much headroom you have. Like that's how much of a gap you had to the to instability already. So you just chewed up that gap. That's part of the reason why stock GPUs and stock CPUs generally come with like 100 millivolts more voltage as their operating voltage than is absolutely necessary for the frequencies they run at, so that there's a headroom for, like motherboard degradation, power supply degradation, chip degradation itself as well. So yeah, there's a reason why there's so much undervolting headroom in every like every chip ever made, is because if you actually ran the chip within 5 millivolts of its minimum operating voltage, it would not work. Like it would be very, very sketchy about, suboptimal operating conditions. So you have to build in some headroom. So chips normally come with some headroom built in. Anyway, so yeah, let's talk about the voltages here. So what I find really interesting is that, yeah, the fake 3800X down here. So now we're just going to use the 1X data. I'm not going to include the 10X data because it's weird, and I'd prefer to be very safe than unsafe, especially with my own 3950X. Like if I have already degraded that 3700X, and I don't feel like I was that mean to that CPU. Sure, it had a couple excursions above 1.4 volts all core, but like it does that on single threaded workloads, right? Why would it be a problem on 4 threads? Because it's off by like, I don't know, 60, 70 millivolts at that point relative to the fit limits. That might be part of it, Buildzoid. Just maybe, Anyway, though admittedly 4 threads of Cinebench is actually relatively okay. That's the thing, is like, but the other thing you need to consider with especially the Ryzen CPUs is when you do static overclocking on these, by specification from AMD, it disables, like, well, if the motherboard is fully following the specifications from AMD, it should disable all of the power saving features. Now, in reality, a lot of motherboards don't go that far. For example, Gigabyte motherboards will often have C-states working, and Asus motherboards as well, and I think ASRock boards do too. And they're not supposed to have those working, but a lot of the time they do. But the other concern is there might be like internal power management features that aren't accessible through the BIOS that do get disabled, because those would be directly under control of AMD. And well, if those get disabled, that might not be, like that might also change the like voltage, like safe voltage margins quite drastically, which is why I wouldn't want my CPU to idle at 1.42 volts, or 1.43 or 1.41 or whatever, like any of these higher voltages that it would actually hit in single-threaded workloads or low thread count workloads. Like I wouldn't want to idle on this because I don't know how much of the chip's internal power management is gone when you do a static overclock. So this, for all I know, is literally being applied to like one very specific circuit in the CPU, and so the CPU is very, like, the lifespan management system is like, yes, we are confident that this is actually safe. Whereas if I whack that, whereas if I change the CPU ratio, because the thing is, like, the AMD CPUs go into this OC mode where all of the power savings are supposed to be disabled as soon as you change the CPU ratio to anything other than stock. So, if you're on a 3700X, you punch in, I don't know, 36 point, like, you punch in 4.1 gigahertz, it's disabled all of the power savings. So now if I punch in 1.4 volts, I don't know that it's like it might be applying that 1.4 volts to things that really shouldn't be exposed to it, right? But I don't know. I don't have control over that. I'm not the CPU. Um, so because of that, my sort of decision with the safe voltages for idle is just like stay below the 8-thread workload voltage, right? Like if you have an 8-core CPU, look at the voltage that all 8 cores will run at in a relatively heavy, like Cinebench R20 in my opinion is not that heavy, but it is, it's pretty, like it's much more than idle. So at the very least, all the cores are doing something instead of idling. So I would just look at, okay, so Cinebench, will run at like 1.36 volts. So I do not want to idle above 1.36 volts because at least with 8 threads of Cinebench running, I know the FIT system considers 1.36 volts and a safe voltage to apply to every single core in the CPU. Not necessarily at full load, because if we're running hyperthreading, then each core is capable of processing about 30 to 40% more data, therefore doing, potentially also burning roughly 30 to 40% more power, which for the most part is just 30 to 40% more current. Which means the degradation is obviously faster and the temperatures are higher. So this is what I would consider like, so my idle guideline voltage, what does it run all core Cinebench? And by all core, I mean without the hyperthreading included. Though I guess if you want to be extra safe, you can look at with hyperthreading included. And then in terms of how much droop I want on the CPU, once we hit Prime 95 128K FFT size, 128K FFT size was selected because it's one of the heaviest FFT sizes out there. There's 3 of them that just absolutely hit the CPU like a truck. That's 128K, 160K, and 192K. All of them are within a couple watts of each other. They're extremely hot, extremely heavy, very likely to crash, cause very nasty transients, yeah, they're great for stress testing in my opinion. But anyway, so 128K FFT size, the CPU, the fit system of the CPU, the lifespan management of the CPU would not go above 1.29 volts. Therefore, I can assume, and this is on a 280 millimeter water cooler with maxed fan speed. So it's not like I'm limited for cooling here. It's just the chip literally won't go above that. So the CPU decides, okay, I'm not going to go above 1.29 volts. Therefore, I will copy that behavior where I'm running 1.375 volts set voltage. So we idle at 1.36, right? So we idle at that same 1.36 that Cinebench actually runs at. But I have normal load line. So when we hit it with 8 threads of Cinebench, it actually droops all the way down to 1.33 volts. This just means our transient response is good, because if we don't have any droop, then I have videos covering that as well. So you can go, I'll link those as 2. You can go watch those. Anyway, so, man, like, you start to realize just how much work goes into, like, setting up the frequency curves and the voltage settings for stock CPUs doing all of this stuff. Like, because there's load line, like, Intel has specifications for, like, CPU load line, and just so many things, and it's just like, well, this is off the deep end. Anyway, so, 1.33 volts under 8-thread workloads, 1.36 idle, and then if we run Prime 95, it drops down to 1.29 volts. It, droops down to 1.29 volts, right? That's because of normal LLC. Alternatively, I could have run something like, say, 1.35 volts with low LLC, which is also a very good transient response LLC setting for the X570 Aorus Extreme. That's the other thing, is actually, if you want good transient response, like, I tested both the X570 Godlike and the Aorus Extreme so far, and on both of those boards, you want a pretty droopy LLC if you don't want, like, really, really nasty undershoot on transients. So, well, depends on the transient. Like, Cinebench doesn't really do much, but Prime 95, like, there's the potential for a workload that isn't as hot as Prime 95, but can have a very short peak current that approaches the same kind of peak currents that Prime 95 hits. And if something like that just suddenly starts up on your CPU, then you want to have a lot of droop, because otherwise your VRM is going to freak out and it's going to cause issues. Anyway, so 1.33. So you know, I've set my voltages according to this for the 3700X. Now, the fake 3800X. So what I find so interesting with this CPU is it doesn't want to go above 1.28 volts. At the same time, it kind of looks like there might be a 40 millivolt offset on the chip because one thread, or 30 millivolt offset on the chip, because one thread, you know, of Prime 95 doesn't want to run at 1.43 volts anymore. But at the same time, I don't know for a fact that that is the case. So I'm not going to go and say, oh, 1.29 volts would be safe because I don't have any proof of that, right? Like my 3700X, because I do have a theory that there's a chance that the really high quality silicon that goes into the CPUs like the 3950X might actually be more susceptible to electromigration. Therefore, you can't run it at similar voltage levels. You know, so that's kind of the thing here is just like, yeah, also like it might be like this is dragged up by the existence of the second CCD. Like the second CCD running drags up the voltage requirements or something. So there's obviously something going on that basically means the good CCD on my 3950X is not allowed, like the chip, it doesn't want to expose it to over 1.25 volts. Which is a lot less than my 3700X. And for this reason, I'd really like to do this test with a real 3800X because I do wonder if it would see the same behavior. Or just ideally, I'd like to have a much larger like range of CPUs to get voltage measurements off of, but I'm not going to go buy every single Ryzen. That's ridiculous. I will probably be buying a Ryzen 5 3600 because I suspect that CPU is going to have some absolutely insane operating voltages that are going to be safe because you have lower current density due to the lower core count, and you also have, well, and probably the silicon quality is just garbage because that's the lowest bin of CPU that AMD's been offering so far. Other than, of course, the upcoming 3300X and the 3100. Those could also be kind of interesting for doing this testing with. But anyway, so the fake 3800X doesn't want to go above 1.25 volts. So even if I wasn't cooling limited on my 3950X, like real 3950X testing, I wouldn't allow it to go above 1.25 volts because apparently the primary CCD is very fragile. Or at least that's the conclusion I'm drawing from this data right here. And to give you an idea of just how crazy the difference in the silicon quality is, the primary CCD of my 3950X at 1.337 volts with normal V-droop is fully capable of running a couple minutes of Prime 95. I didn't do full stress tests, but I can tell you for sure that this 3700X right here at 4.4 gigahertz with this much voltage, it's not making it into Windows. Like it literally, if we tried to get into Windows with that much voltage, it's not making it. So that is an insane difference in the silicon quality right there. And also, like, just the frequency it's such a massive difference. And so I'd also assume that, you know, there's probably a very big difference in terms of how the chip responds to like how susceptible the chip could be to electromigration. Anyway, so 1.25 volts. There's also a chance that this is like the voltage reduction is just related to the higher operating frequencies themselves. Because if you just run a chip at like 5% higher frequency, it will literally pull 5% more current because you're switching the transistors 5% more times per second. And you don't switch a transistor for free, right? Like that's another thing. You don't get to do anything for free. The only thing you can do for free is nothing. If there's no work being done, if there's no state being changed, you can do that without an energy cost. But if a transistor has to be turned on and off, that costs power. So, you know, just the frequency increase, like this is basically like that's almost a 10% frequency gap right there between 4.1 and 4.4. Which the voltage, that's not actually, that's like a much bigger gap in the voltage though. Because that's, that's 20 millivolts. That's like 2%, is it? No. That can't be 2%, can it? I'm not very good at math. Or actually, like, I'm not good at doing math in my head, so I just want to see the voltage difference. No, that's like 3.2% higher voltage on the 3700X. That's does misleading. Like 50 millivolts sounds like a big number until you, 40 millivolts sounds like a big number. That actually that is really close to the frequency gap. Isn't it? Yeah, that's like 7% more. That's like right on top of each other. Like I'd almost suspect that it is literally just going for current at that point. Because if so, the frequency down here is 7% higher, whereas the voltage on the other chip is about 3% higher. And if you don't know this, the relationship, we're just gonna square that. Where's square? Damn, that's really interesting. Well, that does make sense. So, I mean, that still makes sense, though it does make me wonder if you'd actually maybe want to lower the voltage relative to the frequency you're running. Like, if you crank up the frequency, because the thing is, this was run at 4.2 gigahertz. Like, the boost system of the CPU will run, was only going up to 4.2. So if I'm running that same workload at 4.4, I'm pushing 5% more current into the CPU. That is a very interesting thing I did not initially consider. Because initially I was looking like 1.25 versus 1.29, like that sounds like a huge voltage gap, but it really isn't. Like it's very close to the frequency gap. And the thing is, this 3700X tends to run Prime 95 at like 3.95, I think, or like 3.9-ish, which, no, I'm doing that backwards. Man. It's like it's matching the... It's like it's matching the power draw. I need more CPUs to test with. I really need more CPUs to do this testing on. Well, I wouldn't be too worried about exceeding like by 5% on frequency. That's less concerning, I'd say, than 5% on voltage, because 5% on voltage leads to a 5% current increase. Then the voltage itself is cause for concern for certain types of degradation. So, yeah, I'd still feel very confident running that. But that is a very interesting relationship. I really wish I could talk to somebody at AMD about this. But unfortunately, if the funny thing is, if AMD told me anything about this behavior, I'm pretty sure I'd be so NDA'd that I wouldn't be allowed to do a video about it anyway, so it would be completely and utterly useless for me to have that information. That's the best part when it's like, oh yeah, they could tell me why they do that, but then I won't be able to tell you why. But then I wouldn't be able to tell you about it. So I guess, this ultimately works out sort of better for accessibility of information. Anyway, yeah, so like just I guess it's just going according to the frequency gap in that scenario. In which case, I should have, like, for that 4.4, I should have actually lowered the voltage by another, like, 10, 20, 30 actually probably like 30 millivolts. That had not initially occurred to me at all. Oh well, moving on. Like I'd still feel pretty confident running this, because at the same time you have to, like, again, the CPU is going to have some built-in headroom, right? Like I mentioned earlier in the video, there's going to be headroom built into the chip for motherboard degradation, PSU degradation, chip degradation itself. And within the PBO system, it still maintains some amount of headroom, because when you do these PBO adjustments, you're not telling the CPU, hey, remove all of that undervolting headroom. No, you're telling the CPU, hey, you can pull more power. So there's probably there's going to be some safety margin on this voltage still, but that does really make me wonder. Because the funny thing is, and the other funny thing is, at low frequencies, 100 megahertz, like 100 megahertz on a 1 gigahertz chip is a much bigger deal than 100 megahertz on a 2 gigahertz chip or a 3 gigahertz chip, right? Which is, again, like, and we're not even talking about 100 megahertz gap here. It's like 300 here. So, um, yeah, that is not something I had considered. I wonder if that's literally what the boost system is going for. Like that it's like it might be targeting like a certain amount of power per CCD, um, or a certain amount of current per CCD. Either of those two. Anyway, um, moving on. So then we have the fake 3900X, which the voltage goes up a bit mostly because of the cooling, but I think also there's a voltage increase just because we have like potential. Like I'd expect the 6-core CPUs, because I assume the the fit system, the lifespan management system, doesn't just go by how much power is going into the CCD itself, but also how much power is going into each core within the CCD. Which is why you might see some of the disparities, like 24 thread. Wait, no, which one is it? Actually, no, this is consistent here. These are like the same. Oh no, 12 threads, right? So, well, should have matched up more tests like that. 40, like those two are the same. One, like for some reason these are down a bit. This one I don't have a comparison point for. I'm not redoing this testing. Like I ultimately desoldered the DyeSense hookup, so it's like I can't actually, like, I'd need to if I was retesting, I'd need to start measuring with hardware info for everything. Um, and some interesting gaps in the voltages. Though this chip might literally just be running cooler at that point. That's the other issue, is just like there's so like the temperature goes up a bit or down a bit, and the chips will happily, like the chip will pick up 10 millivolts. It'll happily do that, or it'll drop down 10 millivolts. So yeah, the system is very, very sensitive. Anyway, so with the 24 core, like the fake, I mean 12 core, fake 3900X setup, the voltage goes up a bit, which I think is like per CCD current is down. Though interestingly enough, it's still in line with the 24 thread voltage on the 3950X setup. But yeah. Anyway, so if I had a 3900X and this is the behavior it displayed right here, then obviously the voltage match for that would be 1.35 volts, normal LLC, because that way it idles at 1.34, which is in line with the 12 threads of Cinebench. Even without the hyperthreading. The reason why, I mean, without the simultaneous multi-threading, the reason why I do the no simultaneous multi-threading test is because there's a chance that the CPU might decide to juggle some threads around if you have the hyperthreading turned, I mean, the simultaneous multi-threading turned on. And so just to make sure that that isn't screwing with the results, I did do some like no simultaneous multi-threading tests. Anyway, so we have the 1.34 there, so we don't want to idle above 1.34. That's very easy, 1.35 volts, normal LLC. Then it droops down to 1.23 volts, which is not ideal because it's a little bit more voltage. So honestly, I would have preferred more cooling. This is a real, like, this is the other thing that I like to, like, some people might be looking at the voltage recommendations I'm giving here where it's like, yeah, you can idle at like a little over 1.3 and then you want to droop down into like the low 1.2 volt range, like into the sort of, well, it depends on the CPU, high 1.2 to low 1.2 volt range, right? Somewhere into the 1.2 volt range. So a lot of E-droop. And I guess some people might be like, but, like, but the... And so the voltage range here just in general might sound really, really low, but especially with the 3950X and the 3900X, these two chips pull a lot of power. Like, they get really hot and really hard to cool. Like within just like this is just PBO and it's approaching 90 degrees, right? This manual overclock is going over 90. Um, and it's just like, you know, like I wouldn't want to run more voltage just because it would be hitting like 100 degrees at that point. You know, and some people might be like, "Oh, but I don't ever run Prime 95 128 KFFT size," and it's like, well, that's cool and all, but then how do you know that when you get a random blue screen, that blue screen is the software and isn't your system, right? Like that's kind of the thing. Especially like I get like if you have a very specific use case for your system, I think you can probably get away with not using Prime 95 as a stress test. But if you like, because the thing is like Prime 95 is not sort of like it's literally just a program that is capable of doing a lot of math on your CPU very, very quickly. That's why it gets so very hot. And the whole point of having a CPU is that it can do a lot of math very, very quickly. So, in my opinion, especially as AVX 256, like now AMD supports AVX 256, right? It used to be that only Intel had it at full speed, and so it wasn't as popular. But I'd assume over time, these very high power consumption instructions tests, instruction sets, they're just going to get more popular with programmers everywhere because do you know what like one like the whole point like the best way to make your program run faster is to make the thing like if there's any math your program is doing, well, if you can do those math operations instead of one at a time, four at a time, or 10 at a time, or just many of them at once, without having to go all the way to the GPU, right? Because everybody is like, GPUs are great at parallel processing. Why wouldn't you do that on the GPU? Because then you need to go through the PCIe and then no, like I have a program that primarily uses the CPU, and I just want to quickly do some stuff in parallel. So you could potentially end up with a workload that doesn't generally run as hot as Prime 95, but has the occasional blip of load that gets very close to Prime 95 levels. And then it's like, well, if you've never stress tested it with Prime 95, then there's a good chance that that program, like, it might just be decompressing some files or something, and it might just use a lot of AVX acceleration to do it, and it'll just take down your system, right? And you'll be like, oh, it must be a buggy piece of software, when actually it's your glitchy overclock, right? The other thing to consider is that Windows really isn't designed to deal with CPUs spitting out invalid calculations. So if your system is not like 100% stable, you can very much run into like your operating if the operating system is making if the CPU is making minor mathematical errors, the system may not necessarily go down. You're just going to have some very strange unexplained behavior, and over time you can actually corrupt operating system files. Like I've actually and it was like the funny thing is I think Windows 10 is actually much worse at this than some of the older like Windows 7. I've never blown up a Windows 7 install, not with like an unstable overclock. I have blown it up where like I'd throw a bunch of do some stupid stuff with like drivers or something, and then you couldn't get into it because it would just immediately get a driver conflict as soon as it tried to start. um but I have had I've had Windows 10 installs where after, using them for stress testing, not so like while just using them for testing overclocks, like eventually I'd get to the point where I just can't boot that Windows install. It just doesn't boot because I've blown up the OS files. And then you run the auto repair and it tells you it doesn't know what the auto repair says no errors detected, but you still can't boot and safe mode is broken too. And it's just like, yeah, that's really fun to deal with. So, if you have a system where it's because the alternative is if you have a system where you know that you're only going to run like Blender and it's only ever going to do Blender renders, that's all, or just video encoding, and it's never going to run any other software, then yeah, you can probably get away with a stress test, which is like, well, is it stable in my video encoding? Well, yeah, you can probably get away with that. But having a system where it's like it is a matter of time before I come across a piece of software that just takes it down, especially because some people and I'm not, on the level with Prime 95 stress testing where it's like you need to do an overnight Prime 95 burn in. I don't think that's necessary. Like I wouldn't consider that particularly necessary. But being able to at least start Prime 95 without the system going down is a pretty good idea, right? Because if you can't even start Prime 95 without the system going down, that means like a couple hundred instructions of AVX and your system's done, right? And it's just like, that's not good, right? Like, because that means your system is literally incapable of running a couple milliseconds of a heavy workload, which is like, something might just like there might just be something that for a very short period of time does a lot of math really quickly, and your system can't even do that. So, like for my personal system, my criteria is like, and unfortunately, right now my personal system, like my daily system, is not stable. Okay, I am actually very annoyed about that because there is some issues with it where it's like I am not sure if it's my fault or if it's the software's fault. Probably mine, but the thing is, like, the CPU in my daily system is also a degraded CPU, which will get replaced. So at that, like, I'm okay with the random crash every 2 weeks at this point. I've just learned to live with that. I also have a like, I save everything I work on almost every time I make an adjustment because I'm that paranoid about my terrible, well, actually, that goes back further than that. Like, I've had that habit for a very long time of just neurotically saving everything. It's kind of like me mashing delete when going into the BIOS. It's just like, ooh, I've written 5 lines of whatever, save. I've changed the color of this photo, save. You know, so yeah, like, but my personal criteria, if I were to consider my daily system stable, I would consider it stable if it passed like an hour, like 30 minutes to an hour of Prime 95, where I would actually let it go through a couple different FFT sizes, not just 128K. I would probably run something like 16K up to 256K. Just to, give it some range of workloads, because the different FFT sizes give you different transients, different heat outputs, and it just gives you a better idea of that. It's stable across a variety of AVX workloads, not just, hellfire from small FFTs. Which, it's worth noting, small FFTs on Ryzen for static, it's not the heaviest thing you can run. That would be 128K, 160K, and 192K. But yeah, so like a couple, 30 minutes to an hour of Prime 95, variety of FFT sizes, and then I'd also run a similar amount of time of LinPack. And then when it comes to like memory stress testing, I do actually go all the way to 400% mem test. That is just like a bare minimum, like 400% mem test. And then I also do it overnight. I'm not too fussed about like my memory getting overheated by my GPU because I do run an open air test bench, so I don't have hot air pockets in my system because there's literally nowhere for the air to get trapped because there's no case, right? But yeah, that's like that would be the criteria. Well, for a long, until I had this CPU, basically that was the actual criteria I stress tested to. Like, my system was actually stress tested to like an hour of Prime 95, hour of Intel burn test, like overnight mem test, which, depending on how much memory you have, overnight mem test can end up being several, like over 1,000%. So yeah, so I used to actually actually no, before the CPU was degraded. And if you're wondering why the CPU is degraded, it's not actually my fault. I had a glitch, like there was a BIOS update for one of the motherboards that was in my daily system that it's gone through quite a few boards. That basically nuked the SoC portion of my CPU. I think it also probably damaged the cores because I do remember this chip not being as terrible as it is right now. But anyway, yeah, like, so the people who are like, oh, I just don't stress test with Prime 95, I'd say that's not okay. The people who runs Prime 95 overnight, I'd say that's a little excessive, but if you're actually running things like get as heavy as Prime 95, that's probably a good idea. But I would at least, like, you don't want a random, a stray AVX instruction being capable of taking down your entire system out of nowhere. That's just not good as far as I'm concerned. So at least like a couple minutes of Prime 95 and ideally like an hour. Well, not an hour is not ideal, but I would go for an hour, right? So anyway, so because of that, And so if you are stress testing Prime 95 or LinPack or just any really heavy multi-threaded AVX instruction stress test, which LinPack is like OCCT uses an old version of LinPack as far as I know. IBT, depending on like there's I have a copy of IBT that actually uses AVX, but it's still like a pretty outdated LinPack binary. And then there's also like there's an even older version of IBT that doesn't even have AVX acceleration, so that one's basically useless at this point. But yeah, so if you're running any pretty heavy stress tests, like at 3950X at much more than 1.2 volts, is insanely difficult to cool. Like it is stupid hard to keep these chips cool. So that's the other thing is like you might be looking at this voltage recommendation right here and being like, but that's so low, you're not gonna get anywhere. And it's just like, well, if I raise this voltage, I'm gonna run out of cooling anyway, right? Like I like already this is actually not, in my opinion, an acceptable operating temperature that this runs at. So yeah, that's kind of that. Um, so if I wanted to actually daily my 3950X at slightly higher voltages, or well, something like this, I'd probably be going full custom loop, 360 millimeter radiator just for the CPU. Um, that's actually been a thing that I've run in my daily like I used to run in my daily system for a while, and then I decided that I don't need a daily system that's fast that's that fast, but yeah, but full just custom loop, liquid metal, and then you can go to town on your 3950X in my opinion. But otherwise, I would really like you probably just want to run PBO because there's just not that much headroom. Though it is worth noting that this CPU on PBO, regardless what motherboard I run it in, has never done more than like 9,780 Cinebench score, whereas I can do a static overclock with this voltage that runs at, and this LLC, like this right here with this voltage, this LLC, I can run a static overclock that the primary CCD runs 4.35 gigahertz. And then unfortunately there's one, I mean the primary, the best CCX is 4.35, the second CCX is 4.3, or 4.325 or something like that. It's pretty close to the, like, it's like there's one CCD that's just drastically better than the second, right? Like that's the good CCD right there. And it's amazing. But unfortunately, there's also a bad CCD, and the bad CCD does only like 4.25 gigahertz, which is still way better than my 3700X because that thing literally will not start Prime 95 at more than like 4.15, and I can't start Prime 95 on that thing. Like, it would just insta crash when I tried to run that test. Um, so, yeah, that's kind of the thing, is just like, but with per CCD overclocking, I can actually get this CPU to spit out a little over 10,000 points Cinebench. I think it does like 10,100 and something, if I remember correctly. So, it's for multi-threaded workloads, even Cinebench, which isn't even like, the thing is, Cinebench is relatively light, so PBO actually boosts pretty high in Cinebench. But if you had a workload that's like let's say you actually used Prime 95 for its intended purpose and not just stress testing, right? And you wanted to run it on your 3950X, well, a static overclock would give you significantly better performance than letting PBO do its thing, because you would actually have a pretty major frequency advantage. Obviously, in single-threaded scenarios, I don't have a frequency advantage at all. My chip will actually blip up to 4.75 gigahertz occasionally, but in, high thread count workloads, which is what I'd assume you'd buy a 3950X for, the static overclock is actually somewhat faster. So, and more power efficient for that matter, at least up until we get to like 32 threads of Prime 95, because that is actually more voltage. But I'm running Cinebench at lower voltages, so Cinebench runs at less power consumption and higher scores. Because again, within the PBO system, there's still that, undervolting headroom that's built in for chip degradation and the chip, motherboard, and like PSU degradation. It's also as a safety margin for motherboards with really terrible voltage regulators, right? Like there's a bare minimum spec, and the X570 Extreme is obviously not well beyond the bare minimum spec for a VRM for a 3950X. And yeah, and then the same principle, I just apply it to all the other CPUs where like the 3900X, and I'd assume most 3900Xs probably can run higher voltages than 3950Xs. 3700Xs probably like, well, mine seems to be pretty happy at high voltage. I'd assume 3600s probably run above 1.3 volts, Prime 95. Like if you have a Ryzen 5 3600, I would not be surprised if it runs at like 1.32 volts, 12 threads of Prime 95, and then 6 threads of Cinebench. I would expect it to land somewhere around 1.38, right? So yeah, like if you want to run, sort of so on something like that, I would probably run 1.39 volts, maybe even with low or normal LLC. Like actually, I'd probably run something like this, and just because the CPU has less cores, like you can see that with 12 threads of Prime 95 running, there's less droop, right? So actually, I wouldn't bump up the idle voltage. I would just lower the LLC from normal to low. I mean, raise the LLC from normal to low. Normal LLC on the X570 Extreme is the droopiest LLC on the motherboard. And low is slightly less V droop, and then you have medium, high, turbo, and extreme, and ultra extreme, if I remember correctly. But yeah, so that's my thoughts on the safe voltages for Ryzen 3rd gen. Is just you can use the fit system, stay below the, like, I would not idle my CPU above the voltage that the CPU runs Cinebench at for all threads, or all cores. Um, and I would not, and I like, and then as for the Prime 95 voltage, like just stay at or below the voltage that the boost system uses, right? Um, so yeah, that's my thoughts on how this should be done. Because I just don't see any way that AMD would ship because the fit system built into the CPU, like it has to keep the CPU alive for a significant amount of time. And obviously there's the whole like, okay, raising the frequency does actually increase the current draw. Um, that's like, I'm still hoping there's some headroom in that in that area. Um, but yeah, it's just like if you just follow what the fit does, then you should be perfectly safe. Um, because they wouldn't sell you a CPU that's going to up and die after 2 years. Okay, like it's not going to have a lifespan management system that's going to kill the chip after 2 years. That just doesn't make any sense. Um, so yeah, also you should use these PBO limits, because if you try to, like, if you set the TDC and the EDC any higher, it actually glitches out and Prime 95 like voltage like massively throttles down. Um, and yeah, so like that's why I'm using these values, is I've actually tested these values, and with the latest 1004B AGSA, that gets you the highest voltages. If you use an older AGSA, you can actually use even higher settings, and well, I don't have comparison data from that, but initially at least it would run at higher voltages. I assume it throttles down as the temperature goes up as well. Um, but yeah, this would initially start at like 1.22, and then it would come down to 1.19 because this, like, I just didn't have enough cooling at that point. Um, so yeah, and in the future, I am considering very strongly buying a Ryzen 5 3600 to do a sort of more practical demonstration of everything I've just explained here. Like, obviously, I'd prefer to do it with something like with a more substantial core count, but 3600s are cheap, and they're also really, really popular, and, it's just a CPU that I think, like, if you're building a gaming system, you should probably buy a 3600. At the same time, I kind of doubt that the 3600 is going to have a whole lot of overclocking headroom, though I've also heard that the recent batches of CPUs seem to have much better silicon quality. So who knows? Maybe my 3600 is going to run circles around my 3700X in terms of just raw clock speed, not necessarily overall performance. But yeah, I do plan to get a 3600 to do a more practical demonstration of this. But yeah, that's my thought on the static overclocks. Like, I'd still say, unless you're running like, to most people, I'd still say like you're best off just blowing out the power limits in PBO, unless you have an ASRock motherboard, because for whatever, like, ASRock motherboards do strange things for reasons no one can well, ASRock can probably explain, but I can't. But yeah, if you don't have like, for all the other boards, you just punch in them, like, you blow out the PBO limits, and you're gonna get a nice little multi-core performance boost, and your single-threaded isn't gonna change because your single-threaded isn't limited by the power limit in the first place. Um, but yeah, like, and you don't need to worry about the static overclock. But at the same time, like, there are scenarios where I'd say the static overclock does make sense, right? Like, 3950X running 16 thread workload, I mean, running 32 thread workloads, the static overclock is definitely ever so slightly faster. It all is also significantly more power efficient, right? Like, that is 40 millivolts less power for 32 threads of Cinebench. Like, that's a decent reduction in power consumption. Compared to PBO. And you might be like, can't you just undervolt with PBO? Well, yes, but a lot of the time PBO will actually just compensate for the voltage offset, or you'll lose performance, which both are really, like, undervolting with PBO for me has basically not had great results, which is why I don't really talk about it too much, because it's just like, I've not, like, on second gen, it was great. If you undervolted, you suddenly got a bunch of performance out of it. But on third gen, I've tried it, and it's like, at best, nothing happens. Or more like, not even at best, like, most of the time nothing happens. Worst case scenario, you set such a low offset voltage that it actually crashes the CPU. Or at least that's what's been happening to me. I've heard from other people that their CPUs, like, I've heard from some people that they lose performance if they set the offset too low, but mine just straight up crash. So yeah, I'm not sure what's up with that. And I've not seen I've not seen performance losses. I've just seen crashes, and then I've seen a whole lot of nothing changing. So, yeah. Anyway, that is actually it for this video, and, well, it is very, very long. So, yeah, that's it. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comments section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon, which is how I managed to get, like, which, speaking of the Patreon, thank you, patrons, for the 3950X and the 3700X, because, yeah, I wouldn't have those without you. Then also I'll be buying a 3600, so if you're wondering where that's coming from, it's the Patreon as well. Or there's also the AHOC Teespring store, which achieves exactly the same thing as the AHOC Patreon does, except you actually get, like, a shirt or a sticker or a poster in return, instead of, well, basically nothing, except, I guess, like, a good feeling that you're supporting a channel you apparently enjoy watching, which, if you've made it to this part of the video, like, like, come on. It's like, I've had you here for an hour, so at the very least, I'm an effective way of wasting your time. Right? Yeah, there's links to the Teespring and the Patreon down in the description below. If you check them out, I would really appreciate that. And that's it for the video, right? I'm not forgetting anything, so thanks for watching, and goodbye.